warahmatullahi wabarakatuh. Hi and welcome to week 7 of our video lecture, where it will be the last week on the topic of DC circuit analysis technique. So this week we'll be discussing about a few other theorems that could help you in solving a network of circuits in DC analysis. Okay? So the objective and the outcomes of this week discussion is first to understand and apply what we call as superposition theorem. So we'll learn about superposition theorem. And then secondly, to understand and also apply the what we call as Thevenin and Norton network theorem. So Thevenin and Norton network theorem, we'll look at it later. It is basically finding an equivalent what we call as a source instead of having multiple source and multiple resistor. From the point of view of a load, we can create an equivalent source with internal resistance to simplify the analysis of any load. So this week the discussion will be mostly done through demonstration, and later you'll be having your tutorial, of course, to try practice answer those similar questions. So what is superposition theorem? Superposition theorem is basically just another method to if you remember previously, we have looked into mesh analysis and nodal analysis. So in mesh and nodal analysis, what happened was that you look at the component of the network one by one in terms of its component, either by looking at the branch to calculate the currents, or looking at the looking at the node to calculate the current, or looking at the branch to calculate the voltages, and then you look at it one by one through loops or through nodes. But there are other theorems that help you to more or less simplify the analysis of a network of circuit. So the first one is what we call superposition theorem. So what is a superposition theorem? Superposition theorem is, so it is a theorem that is used basically when you have in a network of a circuit, you have multiple sources. So for example, looking at this circuit, we have two voltage sources of one of 10 volt and another one of 20 volts. Of course, you can do mesh analysis or nodal analysis, but there is also this other method where you can consider basically what we call a superposition theorem. So what does it say? It says that the current or voltage in or across any branch can be found by, so current through a branch or voltage across a resistor, for example, can be found by how? By analyzing the circuit with each source separately. So instead of looking at it with two sources simultaneously, we can consider as if the circuit only have one sources at one time. So analyze the circuit with each sources separately. So for example, if you have two sources, there will be the analysis will be divided into two parts, where you will consider one analysis with only the source of 10 volts, and there will be another analysis with the source of 20 volts. So you see, when you have a single sources, then it will be easier to basically to simplify all the resistor in the network to create an equivalent resistor, right? So once you have basically done the analysis one by one, so for example, one circuit, one analysis with only 10 volts, so we eliminate or not consider the 20 volts. So you can see the resistor can be reduced into equivalent resistance. The same goes for when you analyze only with the 20 volts, with neglecting the 10 volts, you can reduce also the resistance into an equivalent resistance. Therefore, you can find, for example, a current or a certain current or certain voltages. Then what you do is, at the end, you can add up the results of the voltage or the current that you calculated of the two analyses that you have done previously. So there is a remark to do that. So I've mentioned just now that we will consider in a separate analysis only one sources, and in considering only one sources, for example here only the 10 volts, there need to be something need to be done with the 20 volt to what I call just now as neglecting or eliminating it, right? So when a current source is not considered, so this here is not a current source. Imagine if it was a current source. If you're analyzing the 10 volts and we are neglecting this source over here, if it was a current source, in order to neglect it, what we do is basically the current source will become an equivalent to open circuit. So this part of circuit will be an open circuit. And what happens if it is a voltage source? If it is a voltage source and we are not considering it in analysis, it is basically equivalent to a closed circuit or short circuit. So if it is a voltage source, if we are not considering the voltage source, therefore no voltage source, it means that the circuit is closed. It is a short circuit. The wire is just connected through. If it was a current source, then it will be an open circuit. So let's try on an example. So here we have an example to illustrate how to use the superposition theorem. So the circuit, the network of the circuit that we are analyzing is over here. So it is the same circuit that we have seen previously. We have two voltage sources of 10 volt and 20 volts. Basically there are two mesh connecting them. And there are three resistors of 1 ohm, 18 ohm and 2 ohm. So the question, what does it ask? It asks by means of superposition theorem, calculate the currents in the network shown. So what it asks for is basically calculate all the currents in the network. So how many current do we have in the network? We can see there are three branches. The branches that goes through the 1 ohm resistor, so we are calling it as I1, and the branches of the current that goes through the 2 ohm, or the current that goes out from the 20 volts, we are calling it as I2. And then in the middle we have another branch that goes through the 18 ohm, so we are calling it as you could call it as I3, but here we know that through KCL this current is basically equals to the sum of I1 plus I2. So from the observation we know there are two EMF, or there are two voltage sources. So we need to separate the analysis into two parts. One part where we have only the 10 volt, the other part where we only have 20 volts. So as we mentioned just now, we separate into two different circuits with each only one voltage sources. So here the sources are considered without internal resistance, right? So it's 10 volts. If there was an internal resistance mentioned in the circuit, in the question, then we would have to add the internal resistance. So what happened here when we consider 10 volts, the 20 volts over here, it was a voltage circuit, a voltage source, I'm sorry. So if we are neglecting it, it is considered as a closed circuit. So you just short circuit it, it becomes just a connected wire like this. And as we mentioned, there are no internal resistance of 20 volts, so we don't add any internal resistance resistor over here to consider the internal resistance of this 20 volts. So the same goes for when we consider 20 volts, the 10 volts is now neglected and replaced by a short circuit. So now what you can do is that we can analyze them separately, right? We can analyze them separately. So for example, let's have a look at this first one. So what we are looking for in the question, it asks us to calculate basically I1, I2 and I1 plus I2. But in separated circuit, I'm going to call it as, for example, here is I1B, I2B, and here therefore I1B plus I2B. Here I'm going to call it as I1C, I2C, and I1C plus I2C. So in the first analysis, we can see that the resistors can be simplified into equivalent resistance. The 2 ohm and 18 ohm is in parallel, and when you parallel them, they are basically in series with the 1 ohm. So the total resistance is basically the 1 ohm plus 2 and 18 ohm in parallel, so you get the equivalent resistance of 2.8 ohm. So once you have an equivalent resistance, so the 10 volt is supplying voltages to the 2.8 ohm equivalent resistor. Therefore, you can calculate I1B. So I1B is that 10 volt divided by the equivalent resistor of 2.8, you get 3.57 amps. Once you get I1B, so once you get I1B, if you look back at the circuit, so we know now I1B, we don't know I1B plus I2B and I2B. So what is I2B? I2B is basically when we look at it, it is if we know I1B and we don't know the current on these two branch, it is basically a current divider, right? It is a current divider. The current I1B is divided into the branch of 18 ohm and the branch of 2 ohm. Therefore, I2B can be calculated using voltage divider, current divider. So here the current divider is basically the 3.57 current from I1B separated into 2 and 18 ohm. So if you want to know I to be, it is the 18 ohm divided by the sum of 2 plus 18 ohm. You'll get minus 3.21 amps. So where does the sign minus comes from? The sign minus comes from the fact that in KCL, I1B and I2B is in opposite direction. Therefore, when you have I1B and you have I2B, the I1B plus I2B is just the sum of 3.57 and minus 3.21. Therefore, I1B and I2B plus I2B is equals to 0.36 amps. So the same analysis you'll do it for you will do it for the second part where we are considering only 20 volt. So you'll get all the currents of I now is I2C, I1C, and I2C plus I1C. Sorry. So the analysis of the circuit separately is just the usual analysis where you can reduce the equivalence into total, you reduce the resistance into the total equivalent resistance, and then therefore you calculate current and calculate current in each branch using either KCL or current divider, right? So the next thing what we need to do is that now we are analyzing two of them separately. Therefore, the final answer on top over here is just the sum of the two analyses. So let's have a look at it. Previously, we have done the analysis separately. So now what we need to do is just to sum up the current. Therefore, I1 is the I1B plus I1C. So we get basically it is equals to minus 2.85. I2 is I2B plus I2C. It is equal to 3.57 amps. And I1 plus I2 is I1B plus I2B plus I1C plus I2C. That gives us 0.72 amps. So you see, the analysis is now simplified by considering it separately. And later what we do is just we sum up or addition the two results together. So if you imagine in comparison to, for example, a mesh analysis or mesh loop analysis, you need to go through KVL, and that might induce you to, and then there is the branch in the middle where you should consider the current loop in this loop and the current in this loop. So usually student might that might induce to an accident, making an error. So using a superposition theorem might be a simplest solution because you don't have to go through multiple loops and interaction of current between different loops, right? So it is just reduction of resistance into equivalent resistance and calculating your current using KCL or current divider. So the next part that was so the one that we've seen just now is what we call as superposition theorem. The next one is what we call as Thevenin theorem. So Thevenin theorem, there is another pair of it, what we call as Norton theorem, that we're going to look later. So what is Thevenin and Norton theorem? Thevenin and Norton theorem is basically also another method to simplify circuit analysis. But how is it done? The theorem says that if you have a network of circuit like this, right? So with any number of supply of voltage and any number of resistor in your network, if you want to know, for example, if you are looking from the point of view of a load, so for example, at this network, we are considering, for example, this R over here as the load. From the point of view of this resistor, so this resistor is connected at node A and node B. So from the point of view, looking at from the resistor at AB, all the network that comes before AB can be considered as an equivalent voltage source or current source. So the whole network can be considered as an equivalent voltage source or current source. So in the case of Thevenin theorem, it can be considered as what we call as voltage source, and later we're going to see at we're going to look at Norton theorem. Norton theorem is basically the same thing, but instead of having a voltage source, we can consider the whole circuit as a current source. So the voltage source here is a constant voltage source with an internal resistance that represent the whole network outside of this resistor load. So what does it say? It says that the theorem in proper wording, it says any network of a circuit with source that is connected to a load R at point AB can be simplified as an equivalent voltage source E in series with an internal resistor R that deliver the current I to the load resistors R. So how do we find these equivalent voltage sources, constant voltage sources with internal resistance R? So how do we apply this Thevenin theorem in this particular circuit? So let's imagine to illustrate how do we use this Thevenin theorem. Let's imagine that we have the circuit, this circuit over here, right? So it is a circuit with a voltage source of E1, multiple resistors, and we are considering the R. So multiple resistors, we have R1, R2, R3, and the resistors at the end of the circuit across the terminal AB R. So we are considering here this R as the load. Therefore, we want to simplify all the other part of the network as an equivalent voltage sources with a series internal resistors, right? So what do we need to do? So we agree now this is the circuit that we're looking at, and this is the load. Therefore, we want to simplify this part. So the first thing that we need to do is, after acknowledging that, is to disconnect the load. So imagine if this was the whole thing was is a voltage sources. Therefore, across AB, AB is the load. So imagine if voltage sources, you can connect and disconnect the load. So let's now disconnect the load. With the load being disconnected, we can therefore, looking at this circuit, we can therefore calculate the voltage across the terminal AB, VAB. So how do we calculate the voltage across the terminal VAB? What we can do, of course, as there is no component over here, therefore there will be no current circulating through R2 because AB is disconnected. So the current and the current is just circulating in this mesh or this loop over here. Therefore, the voltage across AB is also the voltage across R, what we call here as R3. So if you find the voltage across R3, that is the voltage across AB, VAB. So how do we do that? In order to find voltage across R3, we know that voltage across R3 is the product of the current across R3 multiplied by R3. But now, therefore, we have to know what is the current across R3. To know the current across R3, we have this loop, so you can do your KVL, right? So in your KVL, you have E minus VR3 minus VR1 equals to 0. We know that VR3 and VR1 is actually I, is the same current I multiplied by R3 plus R1. Therefore, we can deduce that the current through R3 is E1, so the voltage supply E1 divided by R1 plus R3, right? So that is our current goes through R3. Therefore, the voltage is just the current through R3 multiplied by R3. So here the current is this portion over here multiplied by R3. So you get therefore the voltage across R3, which is also voltage across AB. So as I mentioned just now, since there are no current through R2, so the voltage across AB is also the voltage across R3. So we're going to call it as V, VAB, V over here. So it is equals to E1 R3 divided by R1 plus R3. So for now, that is the voltage across RB. So we now have the voltage sources, the equivalent voltage sources. But it is not just voltage sources. Of course, there are also other resistors you can see. So these other resistors can be reduced or being considered as an equivalent internal resistance to these voltage equivalent voltage sources. So what we need to do now is to calculate the equivalent internal resistor. So how do we do that? In order to do that, so we calculate the resistor of the network with the voltage sources being neglected. So if you want to neglect E1, considering E1 equals to 0, so if E1 equals to 0, basically it means that the circuit is a short circuit, right? It's just like what we have seen in superposition just now. If we have no voltages at all at E1, no EMF, it means 0, therefore we have a short circuit. So now we have a short circuit like this. So from the point of view from the terminal AB, we want to calculate what are the equivalent resistor inside the network. So we want to find the equivalent resistor of this network over here. So we can see that from point of view of AB, terminal AB, we have R1 and R3 in parallel, and then once they are in parallel, they are basically in series with R2. Therefore, the internal resistance R is R2 in series with R1, R3 in parallel. So here we have the calculation of R1, R3 in parallel plus in series R2. So we have the internal resistance, right? So now we have found the equivalent voltage sources V. So or what we call here as the new E. This is the voltage, and R, the internal resistance. This is the internal resistance R. Okay. Now that we have calculated the equivalent voltage sources V across AB and the internal resistance R, we can therefore draw the equivalent circuit, now, such as in D over here. So instead of having all the resistors network and the voltage source, we only have now one resistor that we call internal resistance R of an equivalent voltage source E, right? So E was found from the calculation in B just now, right? And then R, the internal resistance, was found from the calculation in C just now. So for example, imagine if the question asks us to calculate the current that goes through the resistors R. So the current that goes through the resistors R is therefore the current that goes through this single loop. So it is easy. You can do your KVL. So KVL says E equals to VR plus V capital R plus V multiplied by lowercase r, right? So you can find therefore the current equals to E divided by internal resistors R plus the load resistors capital R. So that is calculating current becomes easy from the point of view if you want to calculate the current of the load R. So in comparison, if we have the initial circuit like this, in order to calculate the current in R over here, you have therefore to find the current in this branch. In order to find the current in this branch, you have to do, for example, a KCL over here, or you can do what we have learned previously. You have to do, for example, mesh analysis. So that is that may induce to a certain error when you do a mesh analysis. So instead of doing so, what we do is we reduce everything into an equivalent voltage source and equivalent internal resistors. Therefore, we only have one loop. So the calculation in one loop usually is less risky than calculating it in with a calculation with multiple loop network. Now we have another example of the application of Thevenin theorem. So here, instead of having only one voltage source, we have multiple voltage source in this circuit. We have E1 6 volt, E2 in another branch of 4 volts, and then we have 3 resistors and three branches, R1, R2, and R3. So here we are considering basically R3 as the load, and we want to know, for example, the equivalent voltage across a CD, terminal CD, across the resistor R3, right? So here the question is basically calculate the current through R3. So we know that in this circuit, if we want to calculate the current through R3, we should go into an equivalent circuit where we have R3 as the load, and the rest of the circuit here, the rest of the circuit are going to be simplified as an equivalent voltage sources E with an internal resistors R. So how do we do that? I'll let you go through the steps over here. It is just the same step as we have done in previous slide. So you disconnect the load R3 to calculate the voltage across CD, and then once you have that voltage, you have to calculate the internal resistor. So to calculate internal resistor, you have to neglect or eliminate the voltage sources E1 and E2. So if it is a voltage source, then if you neglect it 0 volts, it becomes a short circuit. Just a connected wire like this, so you can calculate the equivalent resistor. So here it's pretty simple. It's the parallel equivalent resistor. Therefore, you will end up with an equivalent voltage generator with a voltage source of E and internal resistors of R. And then, of course, in order to calculate R, you can use your loop to do your KVL and find the current as mentioned or as written in this example. So please go through the exercise, do it on your own to make sure that you properly understand the Thevenin transformation from a complex network of circuit to an equivalent, what we call as voltage source, constant voltage source generator. Here there is an exercise over here that I would like for you to try also. So here is a more complex circuit like the Hemsworth network that we have done previously in equivalent resistor calculation. So here what it asks us to find is basically the value and the direction of current across the terminal BD, or across the resistor of 40 ohm. So using Thevenin theorem, please try to do this as well. And the answer is basically in the reference book. You may refer to the reference book to find the answer. So we have done with Thevenin theorem. So as I mentioned earlier, in the theorem of simplification of a network, there is we can simplify any circuit outside of the load that we are considering as either as voltage sources, an equivalent voltage sources, or an equivalent current sources. So now in Norton theorem, instead of it is similar to Thevenin theorem, but instead of considering the network, the whole network as an equivalent voltage sources, now we are considering the whole network as current sources. So what is the interest of considering it as either voltage sources or current sources? So the decision on either you want to do Thevenin theorem or Norton theorem depends on what is the analysis that you want to do on the load. So for example, if on the load what you're going to find is the current, then it would be easier to do it. Not it will be easier. The level of easiness difficulty are the same, but it would make more sense to do Norton theorem, because Norton theorem gives you directly the current because it is a current sources. But if you are analyzing on the load its voltage, so it is better, it make more sense to do a Thevenin theorem, because Thevenin theorem give you directly the voltage across the load. Okay, so it is very similar to Thevenin, but instead of having a constant voltage sources, we now have, so here in gray shaded area, gray box, it might be a very complex circuit. I'm sorry, it might be a very complex circuit, but what we are going to do is basically to simplify this complex network of circuit into an equivalent constant current generator. So the theorem says any network of circuit with source that is connected to a load R at point AB can be simplified as an equivalent current source IS. So it is an equivalent current source IS in parallel. So previously it was in series, but current source it is in parallel with its internal resistors of RS, and it delivers basically here a current, it delivers a current IS, of course current IS, but at the load it will become the current IL load. So let's have a look at how do we apply the application of this Norton theorem. In this application, we have the same circuit that we have previously for Thevenin theorem demonstration. To illustrate Norton theorem, here we are going to use the same circuit. So there are two voltage sources, 20 volt and 10 volts, and the three resistors, 4 ohm, 8 ohm, 8 ohm, and 2 ohm over here. So the question asks us for a different thing over here. It asks us what is the equivalent constant current generator circuit for the considered load of 8 ohm and 2 ohm branch. So we are imagining basically in this circuit that the point of view that we are interested in is that we are considering this branch as the load, right? So we want to know here, for example, the voltage that goes across this branch and the current that goes through this branch. So in order to find the current that goes through this branch, all the other components outside of the branch, so outside of the branch you have this 4 ohm and 10 volt, this 8 ohm and 20 volts. The others are going to be considered as here as a current generator, right? So this is the load, the rest are going to be considered as current generator. So how do we do that? So the first thing, what we need to agree upon is that the load is here. So therefore, if the load is here, the rest are going to be simplified into a current generator with a parallel internal resistors. So if this is the load, we are going, just like in Thevenin theorem, we are going to basically eliminate our load. So if it is a current source, if you are eliminating our load, then we are basically short circuiting the circuit, right? So if it is a current source, imagine it is a current source. If you are eliminating this resistor, it means that the current can circulate directly through the branch without the resistor. So it is what we call as a short circuit. So the first step is basically we short circuit the load branch to become this circuit over here. So once we have the load branch short circuited, what we need to do now is to calculate the current in this short circuited branch, or the current, just like in Thevenin, we calculate the voltage across the load. Now we calculate the current that goes through the load branch. So what is the current that goes through the load branch over here? So you can use multiple technique to find IS over here. You can so now what we are doing over here is basically you can use, for example, mesh analysis. But now what we are using is we are using superposition to calculate the equivalent current delivered by the 10 volts. So there's a portion of current I1 delivered by 10 volts, and then there's a portion of current I2 delivered by 20 volts, and IS, the current that goes through, the current of the current generator that goes through the load, is basically the sum of I1 plus I2. So your next task is basically to find in this circuit I1 and I2. You can use, for example, your mesh analysis, but here we are applying the superposition method. And in superposition method, for example, if you are considering these voltage sources, therefore this voltage sources is going to be neglected. It is therefore a short circuit, right? So if it is a short circuit, then the current, if it's the short circuit, then the current, of course, instead of going through two resistor, it is a short circuit over here, so the current will not go through another resistor. It will just come back through the short circuit. That's why it's called short circuit, because instead of going through the resistor, current prefer to go through the path with less resistance. Here in this case there are no resistance as all, so it will go through IS. So I1 is equals to therefore just the current in this loop over here. It is therefore equals to 10 volts divided by 4 ohm, which give us this 2.5 amp. So the same goes for the current I2. Because this is now short circuit, the current of I2 will not therefore go through the resistor of 4 ohm. It will just directly goes into the short circuit area. So the current just circulate in this loop. Therefore the current I2 is the voltage 20 volt divided the voltage across resistor 8 ohm is equal to the EMF 20 volt divided by 8 ohm. That gives us the current of 2.5 amp. Therefore, by superposition, we know that IS is equal to I1 plus I2, or KCL. KCL even is a simple KCL, right? So IS is equals to 2.5 plus 2.5 gives you 5.0 amps. So that is IS 5.0 amps is the equivalent current generator of the network. So now it is not current generator. It's not just the current generator. It's not just current. There is also the resistor over here. So we need to find the equivalent internal resistance to the equivalent generator, a current generator. So what is the resistor? In order to find the resistor, basically we eliminate the voltage sources. So if we eliminate the voltage sources, now it becomes short circuit, and we can see that if it is now short circuit over here, resistor 4 ohm and the resistor 8 ohm are basically in parallel, right? So you have here one circuit, one loop, and here another loop, and they are connected to each other through these two terminals over here, so they are in parallel. So the equivalent internal resistance is basically the parallel of 4 and 8 ohm that gives us 2.67 ohm. So the equivalent network, the network over here, when we are considering this branch 8 ohm and 2 ohm as the load, the equivalent circuit is basically this circuit over here with a constant current generator of 5 amps that was found here, 5 amps, and an internal resistance parallel to the current generator of 2.67 ohm, right? So this is the equivalent circuit replacing the previous more complex network. So the question, going back to the question, for example, might ask us what is the current that goes through this loop over here. So the current that goes through the load branch is basically, it is a current divider. So we have IS, the current of the generator 5 amp divided into two branch, into the internal resistor and to the load resistor. So I is current divider, 2.67 amp current of the generator, 2.67, I'm sorry, is the current from the generator 5 amp multiplied by the resistor of internal resistor 2.67, divided by the sum of both resistor 2.67 plus these two in series is 10 ohm. So we get the current I over here that goes through the load branch is 1.06 amps. So for example, if you want to find the voltage that goes through the 2 amp, therefore V is just equals to I multiplied by R, you'll get, for example, 2.1 volts. So that is the application of Norton theorem. It's similar to Thevenin theorem, but it is basically an equivalent. Instead of equivalent voltage generator, it's an equivalent current generator with internal resistance in parallel instead of series, like in Thevenin. Okay. So here there is another example that I would like for you to try it on your own. So the question here is calculate the current in the 5 ohm. So the 5 ohm is over here. Calculate the current in 5 ohm. So the network are pretty complex. If you want to go through mesh analysis, loop analysis, it is quite long. So what we do is basically we are going to consider this 5 ohm as the load. Therefore, the rest of the current source and the resistor are going to be considered as one current generator. So in other words, what it asks us to do is find the constant current generator supplying current to the 5 ohm resistor. So for this exercise, try to do it on your own. The answer is in the reference book. You may refer to it later, but please try to do it on your own to make sure that you understand the basic principle behind the Norton theorem to find the equivalent current generator. So we have seen both Norton and Thevenin equivalent source. So Norton is the equivalent current generator, Thevenin is the equivalent voltage source. So what we can do now is that once you have one of them, you can basically convert one to the other and vice versa. So for example, if you have an equivalent Norton source, you can convert them into an equivalent Thevenin source. And if you have Thevenin equivalent source, you can also convert them back into a Norton equivalent source. So the choice of using either Norton, which is current generator, or Thevenin, which is the voltage source, depends on, of course, the kind of analysis that you want to do on the load. Either you want to look at the voltage or the current, but both of them are, once you have them, both of them are pretty easy to treat when you are analyzing the load data, right? So but here what we're going to look at is, if you have one of them, how do we convert it into the other one? So in this example, in this demonstration, we're going to consider that we have our Thevenin equivalent source. So here we have the resistance load, we have our equivalent Thevenin voltage source. So the EMF E voltage source is over here, and you have the internal resistance RS over here. So connected to a load, therefore there will be a current load circulating inside that load. So let's evaluate what is the value of the current over here. So in order to evaluate the value of the current over here, you do your KVL. It's only in one loop. So current IL multiplied by RS plus RL will be equals to the voltage E. So you can write the current IL. Current IL equals to the EMF of the voltage source E divided by the sum of resistor RS plus RL. Okay, now what we are going to do next is basically we are going to divide the numerator and denominator by RS, right? By RS. So what is E divided by RS? E divided by RS, we are going to call it as IS. So what is this IS? IS, which is E divided by RS, is basically the current that would flow in a short circuit across the output terminals of the source. Okay, so E over RS is basically the current that would flow if we short circuit the voltage source. So if we don't have RL, if we short circuit it over here, what's going to happen is that there's going to current, a short circuit current that circulates, and that short circuit current is E divided by RS. So we can write our IL in function of that IS by, for example, dividing on top and at the bottom over here by RS. So we found E over RS here is IS. So we can write IL in function of IS. So IL is RS divided by RS plus RL multiplied by IS. So this IS, the short circuited current of the voltage generator, is actually the current of our equivalent current generator over here. So if you want to convert, therefore, if you want to convert from your Thevenin source into Norton source, what you need to do is you just find the equivalent internal the equivalent current generator IS, which is the short circuited current in your Thevenin source. So it's E over RS. So IS is E over RS, therefore you get your constant current generator IS. And DRS, what about the equivalent resistor? The equivalent resistor is the same as RS over here. But instead of putting it in series, in a current generator, it is in parallel. So you can do both, of course, either from Norton to Thevenin or Thevenin to Norton. It's just by knowing that the RS are the same. In voltage generator, it is in series. In current generator, it is in parallel. And the difference of value between E and IS is basically governed by this equation, where IS is equals to E divided by RS. So let's have a look at these two examples over here. So imagine if you have a voltage generator Thevenin source over here with 4 volt and 5 ohm internal resistor. If you want to find the equivalent Norton source or current generator source, therefore you find IS is E divided by RS. So E is 4 volt divided by RS 5. So 4 divided by 5, you get 0.8 amps. So you have 0.8 amps of current source, and the resistance, now you put them in parallel. So if you do the inverse, imagine if now we have a current source. So current source of 0.5 amp and internal resistor in parallel with it of 12 ohm. What would be the voltage source in Thevenin? In Thevenin source, V, so or V or E. E is therefore IS multiplied by RS. So IS 0.5 multiplied by RS of 12, you will get 6 volts. So you can do the conversion from Thevenin to Norton or Norton to Thevenin. So that's all that we have to discuss this week. We have seen, in summary, we have seen in first what we call as the superposition theorem, and then we have looked at Norton and Thevenin sources to simplify our network into an equivalent voltage sources in Thevenin or equivalent current sources in Norton. And then we have seen now finally the conversion between Norton and Thevenin equivalent sources. So there will be tutorial related to this discussion this week, the next day. So please do them, try to do them before you go to tutorial session, and I'll see you next week. So we have completed the title on the topic on DC circuit analysis technique. We are going to discuss next week about now our circuit only includes a resistor. Next we're going to discuss about another passive component, which is capacitor, the capacitance. Okay, thank you very much, and see you next week.